leave on
I'm gonna explain to
Thursday.
you in a little bit, and you don't understand. Trust me.
You were off yesterday.
You don't know the story. It's been a long week. Trust me.
I got my own problems, man. I got my own
PDF.
problems.
Trust me, it wasn't
Get
like
that
my problem.
PowerPoint, he's real into it. I don't
But
know.
it's been his fault. But still, trust me. I'll explain to you later.
Is that what he teaches from?
Haven't you learned how to know learn?
I hate to say it, I've never
Hey,
asked.
I didn't.
Yeah, I will, cause I need to catch him.
I did not do that.
You gotta do like how George and I did. I call him, hey man,
Done?
you wanna hit the
Do it?
You wanna
No?
hit the bar? No,
Okay.
yes? Okay, let's go.
I don't have that problem, that's what I did.
Like y'all girls gonna make plans. Friday, we're gonna all meet up.
And they tell you on a Monday.
I never heard anything about Friday.
I was just giving an example, you know.
You know what? I'm gonna drop it. I'm done. It's a wrap.
Crying.
Everything in the fire, man. Get better results.
Sounds like a great way to roll if you don't wanna tell people you just don't wanna hang out with them.
Well,
I'm not busy, but I may have plans.
no.
You do anything?
That's not how it
Yes.
works.
No, that's it.
That's not how it works. I call you around 5, hey man, what are you doing? Nothing. Do you wanna go to Buffalo Wild Wings? Do you wanna go to the bar? Yes? Yes, okay, let's go. If not, if I do that, I'm busy. Okay, see you later. See, that's the best way to go about this. Nobody has plans,
Kinda out of my
Nobody's being
area
stood up.
expertise anymore with 2 kids in the house.
nobody's, but making plans with girls,
Oh,
you can always expect something to go wrong. 99% of the time. George and I, we make plans. We complete our mission every
It is
single
what it
time.
is. It is what it is.
Every single time. So these girls got involved. Communication just went to crap.
I only have one person to communicate with. I can help it, she dropped the call.
Like I said, George, what do you do? I think
I was ready to do something by 8:30 that night. And I got no one responding, so.
throw this off our game.
by 8:30 in Grove, we're rolling up the sidewalks, man.
I didn't think you guys even went out till midnight, so that was so good.
Friday, actually, you went out. Man, early, I didn't come home till like 1:30.
Yeah, my reward for not having the Saturday class is I get to get up at the crack of dawn and watch my 4th grader go get his ass beat in basketball every Saturday.
That seems fun.
It's fun, but it's frustrating.
I think he feels.
He don't care. As long as he's hanging with his friends, he don't care. He got mad at me because I yelled at him for not diving for a ball on the floor.
Ah, he died for that. Tammy?
Hmm?
Died for that.
Yep.
You know, what's the point of yelling? I didn't
Sure.
people start yelling. It's like, you play them, I'll say watch.
I don't like your attitude.
Yelling isn't good, it's only good.
Printer out there jammed twice. Take a break, I'll have to do some more. Here it is. Actually, I think if I give you my master copy,
With the answers.
I think everybody will have.
With the end.
Let's just do that. Only one short, I was only 2 short. Oh, got, they have one more, oh shoot, I shouldn't have, I'll have to make copies. I do it in my office, that'd be easier. Yeah, I can make my office, I'll get y'all one. So look over that, right there, we'll start that on Thursday. that lab. Notice there's a part, really a part A and B. First part, perform a DC analysis of that circuit and put those voltages in that table like it says there in the instructions and the procedures. And then do a DC load line on it. And then include the work on the next 2 pages, and that constitutes for lab number 1. Lab number 2 should be newer stuff, so it's going to be your AC analysis. So starting the procedure, second procedure there, you should have, you're going to do an AC analysis in that circuit, which you provide those answers in tables 2 and 3. Okay? And then that you're going to move some capacitors around, and it tells, what I wrote down tells you exactly what you need to do. Move the capacitor around, check the voltage out, measure the gain, and then do a AC load line analysis on those, what the answers were in table number 3. Okay? So just follow that. That's 2 labs in 1. So that is actually the only lab you got between now and the test, is that one. Okay. First test comes up pretty quick because it's really a review.
It's 2 weeks from
Yeah, so it comes up pretty quick, which you're looking at the test. That's what's on the test, is that stuff there. So you've got that. You've got what we covered on diodes. That's your first test. So really, it's kind of like your midterm or something last semester is what it really is. That's this test coming up.
You said that tables 2 and 3 are AC analysis?
Yeah, I should say that in the procedures there.
Okay.
So that's all we're doing on Thursday, so some of y'all could do this any place almost. Well, if you had a semi generators. At least you can do the DC anywhere. You can take your little voltmeter out and put it up, see what it does. Okay, questions on that? Hey, it's going to die on it. It died.
See that time of year?
Pile of crap.
And our printer in our office is breaking like once a year.
I know. Thing is, they won't do anything till I call it in. So I got to call it in with the model number and all that stuff to get them to come out here and fix it. It's not like you can't come out and, don't you all do like a PM on it and just come out here once a day and put new paper in it or something instead of me having to call you. It'll go without staples for weeks and weeks and weeks. Thinking, you idiots, don't you know how to do to turn on, see if it's got staples in it or not, instead of me having to call you to tell you. It's not like it's an outside vendor, it's here on campus.
Yeah, they should at least
Yeah, but it's outside.
check on it.
Yeah, if it's an outside vendor, I'd understand.
Like a day. You're getting that many copiers to be worried about.
Really? Okay, let's continue on with our analysis of transistors from last semester, but we're going to go ahead and add a few more new things to it because it's on the syllabus. I want to cover more new stuff. So, so we covered the biasing. The most typical is going to be fixed bias and base divider bias. That's the two that would be most common. Although this semester we'll look at common collector and how you fix bias it, and I won't do common base, but we'll do common collector. Okay, that takes chapter 6, cover the common emitter amplifier as far as AC now. All right, first up, this number here, remember we don't really care, 26 millivolt, pick what the resistance will be. Voltage drop in the circuit here, when the base, emitter, and in that leg drop, but you can measure the current. So here's how it works. If you take the emitter, so if you know the emitter current, for example, let's say it was 10 millivolts, constant at 26 millivolt will give you 2.6 ohms of little RE. That's all it is. You're going to need that. You're going to need that. We're going to refer to that as little RE prime. I like the prime since so little RE prime would be this internal resistance you cannot measure. You just calculate. So it's inside here. That is, this right here would be big RE is what that would have. A little RE prime. We have a big RE out here. There's only one other RE that we need to look at. It's this one. Okay, so when we put a bypass capacitor going to ground off the emitter, we have two places we can put it at, like in this lab. We could put what you would see traditionally, right, a capacitor right there. We don't need that, it disappears. We can do that, which is kind of traditionally what you would do. What that does is all of the AC gets to find a path to ground. So therefore, it's approximately 0 ohm. Approximately, right? X sub C equals 2 pi, 1 over 2 pi FC. So whatever that capacity, as long as it's big. Now if it's a little bitty one like a 0.1 or 0.01, that ain't gonna hold true. As long as that's like some electrolytic and an audio circuit, we're dealing with audios. Most of the time we're going to deal with audio circuit class. I'll let you. So if it's an audio circuit, that means that's low frequency. So long as that's like 100, 200 microfarad or bigger, then we're going to say it's close to 0. Maybe like maybe less than that. We're just going to call it 0. So what that means is here comes the AC. It gets amplified. It wants to find a path back to ground as quick as possible. Well, if we put the capacitor from the emitter to ground, that's like you doing this to the emitter. Okay, it'd be like you ground the emitter. Well, if I ground the emitter, instead of having it go through all those sorry resistors, my current's going to go up. So AC current is going to go up, okay? But what does DC do when it sees the capacitor? Yeah, it just charges it up and it's done, right? So to DC, the capacitor looks like infinity. So the DC current is to force to go up. He won't let me go through here. So it's got to go through these sorry resistors, right? So these resistors are going to slow down the current, so the current, the DC current is going to be lower, AC current is going to be higher. Since the AC is higher, you'll have a lot more gain, because gain is AC. We don't worry about DC, we worry about AC.
Something about a DC.
Well, it hooks up to DC, but it's amplifying audio, that's AC. So AC circuit, you would have the bypass. If it's pure DC, you wouldn't even have bypass. You wouldn't even bother with it. It doesn't do no good. So if it's like a motor, like turning on and off a motor, you wouldn't have. But if it's turning on, if it's audio or, yeah, maybe if you had a high frequency switch pulse a motor, you might have, but most of the time I just ground the emitter there. If I'm turning off a motor, I don't even have resistors. I just run the emitter right to ground. Let's talk about why is these resistors here in the first place? Maybe that's a better question, right? Why is the resistors there in the first place? Well, but if I didn't have the resistors there, I wouldn't worry about it. My gain would already be high. If I didn't have the resistors there, we don't have a problem. This capacitor is not needed if I did that, right? Think of a capacitor coming off there to go to ground. What'd that do? It didn't do anything, right? There's a short there. The emitter's already grounded. So why are we doing this? Well, we just answered it. It makes the AC gain go up. But by bypassing this to ground, it's just like you doing that. So here's the real question. Why are we just not doing that every time? Why are we doing that?
To limit your...
Yeah, but why am I worried about, I can limit the DC current with the resistor on top, the collector resistor. Why do that? It's for matching input and output matching. The top one does the output, those bottom ones do the input. This affects input match. The top resistor, which we'll talk about here in a minute, affects output impedance. It's stability. That's the reason why we do this. It lowers the gain. It raises stability. This right here is not as stable by grounding that. In some circuit, DC, it won't make much difference. But in AC, that right there, doing this, will aid stability, adding stability. So biasing the transistor higher will add stability. Here you go. Here comes an impact. You already know that there can't 0.7, right? So when the signal gets above 0.7, what happens? You're overdriving the transistor. And besides that, the diode is not gonna let it go above 0.7, so just keep driving and driving and driving. So you don't have a lot of room for it to, you don't have room for let the signal coming in do its thing. You're gonna start clipping in the signal coming in. But, watch what happens here. Now, if I have 1 volt in the emitter and ground, and I still have my 0.7 from here to here, what's the voltage on the base now? 0.7 volt. Now, between there and ground, how much voltage do I got to play? 7 volt. See what it does by biasing up the resistor, biasing up the base. By biasing up the base, we allow the amplifier to be able to compensate for a bigger swing, a voltage swing on the input without clipping.
Clipping in my term distortion.
It'll clean it. It'll be cleaner.
It'll be cleaner.
Yeah, it'll be cleaner. So
Yeah.
when you bias it up, that helps. That.
Oh,
That's why we do it. It adds stability. Probably could use another word there, but I like stability. Stability means it works better. But the drawback from stability is you usually lose some gain. You give up gain for stability, kind of like in theory, which one of these things would be the fastest? A unicycle, a motorcycle, or a car? Which one in theory would be the fastest?
Car.
No.
Motorcycle.
No.
Oh,
The unicycle
unicycle.
would be the fastest.
It's like
Why would the unicycle be the fastest?
less
Be on
drag.
wheel.
Less one wheel, the more wheels you have on the ground, therefore you're going to go slow. A motorcycle should be faster than a car. In theory.
Yeah, factory
Don't worry
out
about the motor. A motorcycle should be faster than a car.
You know, if it's a human, it's
Don't even worry about humans, it's remote control.
It's your only
The
control.
unicycle will be faster than a motorcycle, and a motorcycle should be faster than a car. The car should be the slowest due to kind of like a tank, right? Now, they run slow anyway on purpose, but think about the friction there is for a tank. Even if you wanted to go fast in a tank, could go very fast. Now, what, 40, 50 mile an hour, but the
Yeah,
fast
the Leopard,
pans or whatever.
their modern version will do about 50.
Yeah, that's what I'm saying. I think the fastest for a tank isn't the 50 mile an hour. That's pretty fast for a tank. But, you know, the thing will start flying apart if you try to go faster. It just can't frick all that traction. But what do you gain with a tank compared to a car? Stability. You gain stability. I mean, it can't really go anywhere, can it?
You're more concerned with the output.
Yeah, so if I say to myself, you know what, I really don't need a gain of 50. I don't need a gain of 50. I only need a gain of 50. Wow, that means I can make the circuit a lot more stable if I go for a gain. If I go for a gain of 50, then it's not going to be as stable. Now, you know what? It might work just fine. I'm just saying the what ifs. You have a better chance for it to do weird stuff with a gain of 50 than you do with a gain
the
of.
radio world.
I want it as stable as I can get. Let's see if it's the main.
All the mistakes I made.
He's complaining. All right. Okay, so that's what this number is for, because it's going to help us determine gain and stability and stuff like that. Really, that's why you need to know. That'd be the first one we use when calculating. That's why we say 25, 20. Really, both those numbers are wrong. Okay, it's more like about 40, 35 to 40 if you want to get. Yeah, I do. It's all within the tolerance. I don't like you tend to find that the number 40 to 50 because this is ideal. It's never the resistance is never that low. It's probably about 4 ohms. Which would really put that closer to 40 to 50 millivolt. So it's really, in reality, when you all do this in life, you'll find out that the calculated gain is 100, measured gain may only say 75. Big discrepancy. It takes several factors, and I find that so, for the common emitter amplifier, remember we're dealing with common emitters right now, nothing else. For the common emitter amplifier, the emitter goes to ground somehow, either through a capacitor to ground or through just straight to ground. These are the formulas that you need to know. Most gentlemen, so the impedance is approximately beta times RE, or RE prime. So if and by the way, that beta needs to be the AC beta. So let's say you had an AC beta at the frequency, right? Oh, it's good to 100 megahertz, but it has a beta at 10 megahertz, let's say. So here you got a transistor that has a gain of 100 around this. You're going to use it, and you come over here, and you're going to find out, wow, if I put 10 milliamps through it, What's my beta RE? 2.6 ohms, in theory, not reality. So 2.6 ohms times the beta of 100, which you gotta look, that's not even right either, most. So that says the input impedance can be approximately equal to 2.6 times 100, which is 60 ohms. You'll find that your input impedance class is always lower than the output. Do some weird stuff on a common emitter, the input Z is lower than the output. Typically, not all the way. Most time, that's about what I'd expect the input to be anywhere from 250. Now, if you don't like it, 7 ways we can fix it. Watch what happens. It's the exhibit step under your lab. The first time you do this, the first lab, that capacitor doesn't hook up to anything. It's his Mac. I don't want you to hook the capacitor to anything on number 2. It's number 1, number 2, capacitor. Number 3, procedure number 3 is where you start the steps of 1, 2. Okay, so the first one you're going to do this. You already did it. Procedure number 2 is leave that disconnected. You just do an AC analysis of what you see right there, what's on your page. Then in procedure number 3, if you look at step 1, first thing is I'm going to have you tie over here to TP2, right? So you're going to take that capacitor and go ahead and hook it up to TP2. Do all your AC analysis. You measure your voltage out. Once you're happy with all the results there and record everything, then you're going to disconnect and move it up here to TP1, which is full, we call it full bypass. That's full bypass, okay? Right now there's no bypass. No bypass. We put it right here, we have partial bypass, and then we have full bypass. Okay, from here just a basic analysis, and you already see the basic formula. This is a shortcut formula, all right, we're going to add to this, but this is good enough for right now. That's good. You can already see if my Zi is equal to beta times Re, that's assuming what? The emitter is 0. The emitter goes to ground. So which one of these, this one, that one, or that one, which one of those 3, 1, 2, and then nothing, which one of those 3, 1, 2, or 3, makes the emitter 0?
1.
Number 1. Very good. Excellent. Class. Excellent. All right, so if I hook the capacitor right to there, that makes the emitter look like it's shorted, doesn't it, to AC. So look at the formula when you stretch it on out now. See how the formula is grew? It's going to grow here. It's going to get bigger than that. But look how I just made the formula grow a little. R big E, all that resistance. That's R big E, right? But because you shorted, and this is AC, never think of AC and DC the same, only AC. You put the capacitor from the emitter to ground, that resistor looks like it vanishes. It's gone away. Because 0 parallel to anything is 0, right? So guess what happens to RE? It's gone. You don't add it. That'd be a mistake on the test. You don't add that. There's nothing there. So there's your formula right there. That's with the emitter shorted, or emitter grounded, or emitter bypassed, then that's what you use. All right, now watch exhibit number 2. That would give us most gain, by the way, to figure that out. That's going to give you most gain. Let's say your gain's super high, or you don't want your input impedance to be around, you want it a little higher. You do that, see? This gives you the best of both worlds. Let's make this top one 50 and the bottom one. Let's see what happens now. The bottom one's bypass, but this one here is not. So this resistor is killing some of your AC gain. It's killing it because the AC's got to go through that 50 ohm resistor just like the DC current did. So the AC current and DC current. So we're gonna split these up in designation. That's anytime you're dealing with DC, everything's big letters, right? So this is going to stay big R, big E. It's still going to stay big R, big E. I want you to label that one now because it's got a new role. Before it was big R, big E, but now we're going to change. That becomes big R, little e. That's big R, little e, and that's just little re. Okay, so now you got three letters there. Little re, big R, little e, and big R, big E, because that's DC only. That's DC and
Using the DC.
no, we're still AC.
AC?
Yeah, I'm still going to label that
Why?
big R.
I mean, didn't you say that the bottom R big E? Why
Because
is it not
okay,
0?
this is biased up with DC to make it work, right? So DC current's flowing the DC circuit whether you hook up AC to it or not. So right now, let's say there's no signal. It's just an amplifier sitting on the bench. You're not even, but you got power on it.
Oh,
So you got DC current going through here, but nothing's happening yet. But as soon as we apply an AC signal to it, now that guy is going to limit both the AC. So you label it in its function of AC, not the function of DC.
Just to make sure I got this clear though, but if you get both of them in line without that bypass capacity.
Oh, we're going to get that in a minute.
Okay.
Let's get that in a second.
Okay.
That'd be my third step. not on your home, not on your lab. I'm going backwards from what's on your lab, okay?
Yeah.
Because we're adding to the formula. This formula applies if that emitter is bypassed to ground. There's my bypass. When it's bypassed to ground, or you got it directly grounded, that's that formula. Step number 2 would be right here. See that? Now I'm going to add what to this up here? 50 ohms at 2.6, which is 52.6 times 100. Now look what that did. See that? Big difference, wasn't it?
Yeah.
I went from 200 to 300 ohms to about 5 kilo. Big difference. Now, in reality, it won't be that high. It'll be lower than that by about half. It'll be about half that in reality, which I'll show you. But still a lot higher. And still, that's going to give me low to medium gain. Now look at the last one. No bypass at all. 100 times. Now, here, you are okay in this class to do. I would have done it up there too already. But you're okay to do either one of the times to do this right here. I'm going to show you. Class, if that's only 2.6, and that's 50, and that's 50, well, of course that's up to 2.6 of 100, very much. So guess what? You can just do that. It'll be close enough on the test. Just do away with RE prime. So unless the emitter is fully bypassed, you can almost flip out that little RE prime, and you'll be close as anybody else. So really, the only time that you need to be, well, I want you to calculate RE prime, but when you finally do the whole problem, you might see that, oh, that emitter is not fully bypassed. There might be a stabilizing resistor there. This one here's the this one's called the stabilizing resistor right here. That one there's just a little bypass. That's if I didn't need it, then I would just put a 100 ohm in there, right? If I didn't need a stabilizing resistor to do this, right?
You just use 100.
Yeah, that's what I would have done if I was going to either do this. If I was going to do that, why have 2 resistors? I just use 1 resistor. Or if I was going to do that with no capacitor at all, then if I'm going to use 2 resistors, there's a reason. The top one will be a stabilizing, and the bottom one will be just standard. So that's going to run the impedance. This right here has very low gain. So I'm going to jump to that right there. Jump to, well, the output impedance is basically equal to what? RC. That's your output. So let's say you picked let's say you had 1,000 ohms or you got a 1K. Guess what my Z out is equal approximately? 1K. That's how you do it. That's the transistor's impedance. Great question. Did you hear what he said? The internals to the transistor is near infinity. It's really not. It's probably like a megohm or something. But what did we just say about the emitter the internal emitter resistance? You can kind of like ignore it if what? You didn't have anything bypassed here. Now watch this. If this internal here, let's even give it let's give it 100K. Let's call it 100K. All right. So let's say there's 100K of RO. RO would be my RE prime here. RO is the collector side of the emitter side. You see what I'm saying? So draw a line. That side is little RE prime. This side would be little RO prime. See, we hardly ever talk about RO. I'm going to show you why. If RO is as low as 100K, which I doubt, I bet it's higher than that. Let's just say it's 100K. I'm going to prove it for you. Let's say it's 100K. Normally, your resistors up here in the 1 to 10K range. Never, very seldom much over 10K. It's probably 1 to 10K, maybe even low. So let's say that resistor's 1K, which is kind of typical. 1K's there. 1K, 2K, really nothing about it. Well, if that is from there to there, then it looks like a what? It looks like a shunt going to ground of 100K. Now, if that's 100K in parallel with 1K, what's the ratio? More than 10 to 1, right? About 100 to 1. What did we just say here? If the ratio was much above 20, 30 to 1, what am I going to do? Flip it out. If I'm going to flip it out, what can I say? The output impedance approximately equals RC. That's why. If you don't believe me, just go through this right here. There you go. 100 times 1 divided by 101. You'll see that it has very little effect. So when you see that, that just means this is the transistor model. That just means that the internal impedance of the transistor on the collector side is kind of high. The impedance on the emitter side is fairly low. So let's skip that. Let's go to that. So let's go back to our 1K up here. So we got a 1K up here, and let's stick to the 100 ohm down there. All right. And like right now, let's go back to our 250s. We still got 100. Nothing's schematically. Okay, so we got 250. All right, if I do this right here, RL over RE, what do we have up here? RE prime plus RE, right? So the top is a 1K, right here, because 1K by itself. We don't worry about the transistors and P, just use RC. So RC is 1K. So 1K goes on top to find AB. Remember, A is gain. And the bottom is 100 plus the 2.5, which I'm not even going to bother with. So 1K divided by 100 is, my gain is probably, in reality, guess the gain really is probably about 6 or 7. Remember I told you that 26 millivolt network. So in reality, if you went over and built this circuit and checked it in the lab, I would bet your gain's probably closer to 7 range. I always think about that. You will not have over a gain of 10. It'll be between 5 and 10, probably closer to, okay? So when you do it in the lab, you go, this thing ain't adding up. Well, it probably won't add up. You just need to realize the difference between your lab analysis and your math analysis will be a little skewed. The volt DC should be right on the money. AC where things start kind of, you can't account for all the. Now let's bypass. Let's put a capacitor right there to ground. Guess what happens? That drops to what? 50. Now my gain is 20. It's going to be less than 20. It's going to be probably about 18 or 17. Now let's bypass both of them. Now we can't have 0 there because that'd be infinity gain, right? That's where you got to go back and do beta times RE. And earlier we calculated 2.6 times beta. So that's what? 6 is RE. There's another formula. So 1K divided by 2.6, what's that gain? Yeah, and what will it be in reality? About half of that. As you go up in gain, the difference between the two gets worse and worse and worse. So I would bet that if you built this in a lab, your gain ain't over in reality, but it calculates a whole lot more. So kind of keep that in mind when you go build this stuff in the lab, and as the circuit's gain is supposed to be going up, it will go up, but it ain't going to go up as fast as you think it is. It's actually going to do, it's going to have like Moore's Law, the opposite of Moore's Law. So it's going to look like this. Instead of it being linear, it's going to do this. Okay, it's not going. The gain will not go up the same rate because there's other
Gain of it?
Well, 1K divided by 2.60.
384?
Yeah. So in reality, it probably won't be over 100. But I usually about half. Right. I've seen 150 to 200. Never. Ooh, right. What can we draw from all? What if I want more gain? What would I do? In other words, I got the bypass capacitor there. Everything's set up as most as I can get it. From what you see right now, what is the most easiest way to get more gain?
A low resistance value on your emitter.
Yes, I can lower it, but that's great. I can do that, but what if I already have a bypass capacitor?
Change the resistor at the top, the 1K.
Ooh, I could raise it or lower it. Raise it. Yeah. If this went to 2K, what's 2K divided by 2 points? I just doubled it. Now, something else is going to happen. What else happened? This is what I was thinking about before. I would have done something else.
You do that, you mess with the bottom and
No, we can make it.
you can, but it's not stable as it is though.
No, but I can add a little bit of resistance in here and add to get some stability.
I think you'd have to change it.
Yeah, I'll have to change it. But look here, if I raise this or raise or lower that.
Lower.
How would I lower that? Run or current. See that? So if I can run more current and raise that resistance, now something's not given here, right? If I raise resistance, what happens to current? It goes down. So if y'all raise this to 2K, what's going to happen to that bottom resistor? I'm sorry. You raise this to 2K, that's going to cause that to go down. Going down is going to make that go up. If that goes up, guess what? You just killed your net effect. That's what I was wanting to get to. So how can I raise current and raise that resistance at the same time? Only one thing left. Run voltage. So if I run a higher voltage, I can increase gain and put more power.
That makes a lot of sense.
Because P equals what? E squared over R, right? So if I run more voltage, I can get more power out. Now you know why people like to run vacuum tubes has some advantages. So we run such high voltages. If we run high voltages, we have higher impedance. So we have real good voltage.
Is there a protection there? I mean, wait, if you raise the voltage, do you have to change anything else in there?
Yeah, you redesign the circuit for the higher operating voltage. But transistor won't know. As long as you got protected, you're within its range. Let's say for like a 2-inch 22-inch, I think it can take 30 volts, maybe even higher. I think it can take over 30 volts. So as long as I make sure there's not more than 30 volts peak to peak going through it, then I'll be okay. So that means I just run the bias up, run 24 volts up here for VCC. Midpoint bias, I put what? 12 volts from the collector to the emitter. That'd be midpoint bias now. That's well within the range of that 22. Reason why we do it, because we don't have 24 volts. We only have 12 volts. So you're limited on your voltage swing. But if I run the amplifier at higher voltages, I'm not limited as much in my voltage swing, so I can get a lot more power out and have better linearity with higher voltages. Right now, the trend classes run higher voltages on everything. That's a trend that's happening. I got in my first ship some part from across the pond.
So they use buck volt, they use those buck
No, I didn't get
inverters?
that. This is another order that I told the guy what I got from didn't work, and I either want a refund or just give me something. So he gave me something. So I asked for an amp. I got a 60 watt. I got two of them. I'm gonna keep one. 60 watt amplifier, single chip. It's mono. It's not a stereo. It's 60 watt amplifier. The whole thing's that big. It has to have two powers. There's a way of faking it out.
Two difference?
No. Watch how I'm going to do it. And this is how you would do an amplifier here. And to you, it's going to go, what the heck? There's my negative, right? Out of the breeze.
Is it voltage doubler?
Now the capacitors will charge up. These two capacitors, let's say there's 20 volts here. There'll be 20 volts across both, right? But what's in between? 12, right? 10 volts. So there's 10 volts across that one, in series with the other one. So there's 10 volts here, 10 volts there. But that 10 volts is more positive than that side, and that side's more positive than that side, right? So that makes a voltage divider. The voltage divider is your ground. You do not ground that negative. It stays floating. If you float the negative, where's ground? You don't have a ground. You can do your op amps the same way. You can float the ground where ground does not connect back to the power supply. You don't ground the negative. You float it. So by floating these two, they're in reference to ground. What's ground? Well, now you're going to assign a ground, and guess how I'm going to assign the ground? A voltage divider. So, from ground to here, that's more positive, right? But what is ground to there? More negative. You just made yourself a cheesy dual power supply.
Does it want 20 volts?
My circuit wants 20. Actually, it puts out a lot more power at 30, and the more you run the volt, it can go up to 6. I think the minimum it can run on is plus minus. So plus minus 12, it will work okay. But remember what we just said? The lower you keep your voltages, higher output for 30. The chip, it's a positive, negative volt. I hook it up. The ground, like your return line for your phono plug, all that will hook to that center point. So the center point is not negative and it's not positive, but it's a center point. It's called a chassis ground. So this will become a chassis ground that only the grounds from the circuit get tied to, like your phono.
Did you shock yourself?
No, you have to complete a circuit. So let's say it was 1,000 volts there. Yeah, if you touch that, grab a hold of that, yeah, you get shocked. But we're only dealing with 30 volts here,
Just
so.
touching the chassis with?
No. It'd be like, this is grounded, right?
Yeah, then you touch that.
Yeah, that's right, if you had separate supplies. So if this negative was out there someplace else powering something else, then yeah, you'd have but the negative only ties that chip and that's it. It doesn't hook to anything. You just don't ground that negative. Just think of the capacitors of the voltage divider. It'd be no different than you doing this. What if you just took the capacitors out and put a resistor there and a resistor? Well, what do you got? Voltage divider. So from your voltage divider, if I grounded the center there, that would make that more positive than the center, so that'd make it slightly positive, and this would be slightly negative. What's the problem with that circuit? Well, the problem is your resistors are going to limit current, right? So you won't get as much current out of it. Capacitors are going to limit current. They don't let, remember DC's getting blocked by a capacitor, right? This is only an AC return. I only need an AC return. Well, AC looks at those capacitors as a short circuit, not DC. So it's just enough biasing in DC to power the circuit, but the AC doesn't. Mirror AC to the capacitor looks like ground. It's supposed to work. I'm gonna find it. I'm gonna bring it up here when y'all are building your little amps. I got my own little amps to build, and y'all are gonna get to do some of these too. We're gonna make some printed circuit boards, and y'all are gonna make us. I'm gonna give you that. I got tons of parts. Gotta give away some y'all bought.
Ask him after class.
So, and if you don't have your part parts organized like that, just go get a fishing box like these. And, yeah, I already took them home. Sometimes big parts like this, I don't mind them just laying in there. But when they start to get like, these are not too bad. Those are surface mount lytic. Those are not too bad. But once I get down to these little, I don't like them just laying there. Because if I drop this thing, they're gone. So this is what I do. You all might have your own method. I leave surface mount resistor capacitors all on the reels like that. I leave them there. I don't take them up. If I don't use them a lot, in other words, I'm not using like 20 at a time or something. It's only like 2 or 3 at a time. Then I'll leave them like that. I'll take some colored Hermes. That's kind of my color coding method. So I'll take one section and all those will be green. I'll take those sections and all those will be orange. And then I'll go along the back of it and write down like 1K, 2K, 3K, or 0.1, 0.01. So that way if they got out of place, I just look on the back, is there one stripe of color? Then when I run out of colors, guess what I did? I do double stripes, right? So I kind of, so I don't have to see the number real quick. I can look at the colors. I do that. Now, if I don't keep them on the reel, or I got them when they weren't on the reel, then I do like these. Those are filled. I bought those in California. There was these wholesale people. They didn't know. I think they were. So I got these, and they just came in a bag. So let's say I actually wanted to use those for something. I wouldn't keep them in this bag. I use contact, little contact glass. Okay, I don't work on a wife for it. So the little bottle, glass little bottles, the contact come in. They even oh.
You're right out here.
I thought you was talking about this little screwy things.
Oh no, I got it.
Anymore.
Okay. Do they still make them?
You can, yeah, but they're more about this stuff
Yeah,
now,
that's what she's
term,
got.
so I don't see those
Okay.
anymore.
Probably that's why I don't get them from her anymore.
I have those bottles like you're.
She's not mad at you.
Just put them in baggies.
Yeah, bottles, but I like to set them up. So when I'm building amplifiers, I built up a little wooden plate that big, all right, and on top of it, I took a piece of 1/4 inch high stop, about that high, about 2 inches wide. I chucked it up, and it's about that long, about the same length as my board. I chucked up in the mill, and I ran a wide bead down that circuit board. So it's sitting like that. The bead is not like 1/10 of an inch deep, but it keeps it from wobbling out of it, right? And that worked really good till I designed different board sizes. Well, just had to think about it. Is it smaller or big, right? Well, some were smaller. Well, I just went down with the mill and ran another bead, another 1/10 of an inch deep, just enough to keep it in the line. So this thing holds like 3 different board sizes that all of them fit in my little channel. And so I can line up about 10 printed circuit boards in my little channel. It's about that long, sitting on top of a wood board. Well, this only is about that wide on the wood board. I got all this wood space in front like that. I drill holes in the wood board. So now if I'm doing a project, I don't want to keep reaching over this, I dump the parts in those little wood holders. Well, yeah, and then what's nice about the little glass bottles, that's the ones I use a lot of, and I don't want to keep tearing them out of these. So I have like maybe 10 of those glass bottles, and you know, she wasn't getting this for a long time. She wasn't getting that many, so I went to her and I got the same person. I went to her and said, hey, you know those glass bottles? You can get rid of. Oh yeah, we throw them away all the time. I go, well, yeah. So he loaded me up. I had like 100 of them. Now he had to strip the label off. Apparently it was against some sort of law. Oh, okay. Yeah, they were all gone. So that's all right. I soaked them in acetone. Thank you. I soaked them in acetone to get all the stuff off. I didn't want to know anything. So I took them, soaked them, and did that. And what I put in those is my bulk one. So let's say I just don't go buy 100 of these for like my .1s. I try to find a reel, the whole reel. And I've got some reels over there. So using on a reel, you get like 4,000. Okay. Now, if you went to Mouser or DigiKey and bought a reel, that's going to be about a penny a piece, penny to a penny and a half a piece. So it's going to cost you between $400 and $500 for that reel. All right. I don't want to spend $400 or $500 for the reel. Like this dude here in California, I was able to get a whole reel up from him for like $80. They got scrapped out. Company don't know what they're doing. They scrap them out. I got all kinds. I got reels over there that only cost me like $5 for the whole reel. Now there's something I really can't use, like 1Ks. I can only use so many 1Ks class. Usually about 1,000 I'm done for a couple of years. So they just kind of get stuck away until I run out of them. I go get more. But like capacitors, like a .1, .01, I want thousands. So what I'll do is I'll get a piece of paper like that, crease it. I'll sit here and just go zip like that. Just keep pulling them apart. They'll fly off and hit something. I try not to get too worried about it. I used to go look for my little part that fly off, and I thought, I'm spending 10 minutes finding it. I started realizing, how much that part cost me? I slapped myself. Stupid. You're wasting. You spent more money looking for the dumb little part that flew off. So anymore, I screw the part. Okay. I don't get false in my life. I either flip it off anyway now. So I just, you gotta take charge. You can't let the little part get you, right? So I start flipping these things off, and now I got a whole pile on a sheet. I take my crease, I pour it in those little eyeglass until I fill it up. And it's usually about 300 or 400. But that way, I got my little tweezers to reach in there and grab them out instead of having a dink with pulling these apart. Because when I pull these apart, I usually get one flies off, and I gotta go find it. So it's nicer to have them in a bottle, but my bottle chest would take up the whole thing if I did that. It's easier to keep them at this until I need it. It's like, but if it's a whole bunch, then a bottle. And they're mostly all surface mount. Big lead just stay out like that. You know, they're all right. The little surface mounts. And then it gets kind of gnarly. Like here's what I'm talking. See, those are surface mount electrolytic. Well, that's okay. I mean, I've got like 10 on a string, 12 on a string, and I got room in here to do that. Well, I do these based on the circuit I'm doing. So this is just leftovers for you all. But this class, probably most stuff's mine, and I make a bunch of those timer boards. Remember for the bot? So I make a bunch of those up, and I give you all parts out of it, and I'm kind of done with it, right? So that's kind of what the little kit I made up. My other one's for my preamp, so I got like 3 or 4 of these for different things, but I ain't got enough room to put all the parts in one. Well, like the other day, I bought some surface mount inductors. I'm really getting in. I got some, but they're little bitty. I use this. These things get kind of gnarly. So I got a roll, and it coils up. When I undo, the coil goes everywhere. I can't fit it back down in there unless I cut strips. So I'm running out of room. At night, I found all those little glass bottles. I said, forget this. I started ripping them apart, and I got 50 in a bottle, about the most I can get. But 50 should keep me for a couple of years. And the rest of these, I'm just going to throw in a drawer. Forget it, plastic stuff it full. Probably I'm getting that way.
Buy some more.
I bought some more. You know, I bought.
Yeah,
It's
that's
getting bad.
best feeling in the world.
It
I got
is.
that at the house.
What did I buy? I don't remember what it was. So a brass pipe, antennas, I made sizes.
It was a good deal though, I bet, right?
Oh, well, yeah, of course it's always a good deal. Now it cost me just as much as it did the last time, you know. But I was trying to get to that $100. So if you need a $100 minimum one-line metals and on, because I use it so much, I get 25% off. Like a 2-day window, I'll get an email like tonight. I got the next 2 days, I get 25%. Which, you gotta watch those places, because it just pays for your, it basically pays for your ship. I also found that that place doesn't do you a good deal on plastic. I ordered some One Sure Virgin Teflon. Theirs was $36 for, now that's, but now the brass and copper from them, they're only a little bit higher than I can get at low, because they'll cut it any length, no minimum order. So I didn't get my brass from them, but the plastics I get some plastic. I called the guys over there because I get a lot of stuff, polycarbonate and all that stuff, or advanced plastics. So I came back. Oh, that's $8.50 a foot. So you're kidding, obviously. Yeah, you got to pay tax, but guys, I'm gonna tell you. Yeah, if you order off the web, you don't pay a cent in the state of Oklahoma, which is almost every state, VAT tax value, which is really their way of saying we're screwing you whether you buy it out of state or declare that. The good thing is, though, to cover your butt, if you haven't done it in a long time, is if you look at your tax in the long form, it's already added in.
They know?
No, they just did
No,
it
it's
for
just
you.
automatically.
You got to fight it. You say
Oh.
no.
I didn't know.
Yeah, it's in there.
They already throw
It
out.
works out to be about $100 to $200 on your taxes.
What?
Yeah, it is.
Now on my like TurboTax, it pops up and says, "Did you order anything?" And I,
No,
of
Yeah,
course,
if
say,
you
"Hell
say
no, I
no, then you're basically telling them zero.
no.
But most of the time, because they know how people shop nowadays, they will probably not agree with that unless you got proof. I mean, you better. So if you
it's
get
still
audited
like-
and
yeah.
you really did buy online, you're hosed. So you know
Well, how are
what,
they gonna know?
class?
Yeah, but
Take.
How are they gonna know?
Receipts to prove that you bought
They
it?
have
check
the-
your,
They have the
online
power to
records.
subpoena your bank records
Yeah,
if
your
they
bank
want.
accounts.
Yeah, but
You use PayPal? You're hosed.
I never, I've never used it.
They can check, they can find out.
But They also said that their kind of
That's the
chances
feds.
of being audited this year is very slim.
That's the feds, that's not the state.
Well, I
Just
just,
keep the 200.
I'm being more on the cautious side more and more. I used to not care 20 years ago. 10 years ago, I started caring a little bit. Now I care a little bit more. So it's just when you got more to lose, you should care more,
If
right?
you're someone who's not buying online, okay, that's cool.
Yeah, here's my
I don't buy
logic.
online.
I buy online more now than I used to.
My logic is if you're a heavy purchaser or you run a business, you're gonna get audited.
I run a business,
Yeah.
and I buy a lot online. I mean, I used to be a devout Radio Shack goer, don't get me wrong. I went to Radio Shack and buy parts and all that stuff in the 70s and 80s, but I'm carrying what I need and have a good selection. These places like Mauser and Ditko, those are the three I use a lot. They started showing up, and I used to feel bad.
Are they like
No,
exclusive companies?
Radio Shack can't touch what these. You want a
Yeah.
part, they have a part. I mean,
No, but that's normally how happy you feel with the idea and making.
Radio
it
Shack's more
better.
retail stuff. They didn't get into, they didn't have people, they didn't hire people that knew they were their part. They go, oh, it's on the shelf down there someplace. I mean, that's their,
Yeah,
they
that
weren't
is
weren't
true.
parts
They're
people.
annoying just to walk in and
But
say
a
hi.
lot of what they were geared towards was consumer stuff anyhow,
Right,
so
exactly.
once
But in the
once it
70s, it
went
wasn't
away,
that way. You can go and buy kits. You could buy. It was half electronics, like for us
Yeah.
techies, and the other half was maybe some stereos and
Yeah,
little
they
fish
didn't-
finders, or
they
you
didn't
know.
really
I
do
kind of
that
vaguely
stuff
remember
until
when it was still that
the
way.
90s. That's when-
When they came out with the Trash 80, when they came out with the TRS-80 computer, that's what started, and I'm not saying it wasn't a good idea, it made them a lot of money for about 5 years. But when the PC started coming down, why would you go out and buy a Trash 80, right? It can't compete. So they tried to compete for a while there in the late 80s, and they were getting eaten up. Well, the rest of their profits, just, I think after that, it just kind of, because people stopped thinking about Radio Shack, about building stuff, they thought about more about computers and maybe cell phones and things like that, and game, and they lost their base. Well, I mean, if they're trying now. I mean, they sell Arduinos, y'all know that? Yeah, I mean, they're trying, but I've kind of already left and went away.
You
The
would,
one on 71st Street's everything happened.
They're closing
Really?
stores.
The one
Yeah,
that
they
went-
are, like, I forget how
Yeah, I
many
saw that
thousands of
sign.
stores.
There's
The
somebody
one from
standing
here.
outside with a sign telling.
Where
people
at?
to
The
stop.
one in 71st and,
Really?
yeah.
And there was, even on
Everything's
71st
all-
Street.
I'm
there
gonna go
was-
in there and look at it. I can get an
I don't
Arduino
think so.
for half, I'll take it.
Well, even there with Rushmore and Hill.
That one too?
There was jumping around,
Yeah.
the sign was-
I'll go check them out. Now, they could just not take that merchandise, put it in the stores. So probably the stuff that's in there is probably not stuff you
I'll
get.
take a big bird board.
Yeah.
probably depends if they're franchisees or companies.
Yeah, the one in Sand Springs was individually owned. I know that's one. I worked for one for two of them, part-time at night. And I worked for the one over at 31st, and it's not there anymore, 31st and Sheridan. Used to be one in there.
Is that
I just wanted to work money, Christmas money. I'd start November 20th and work till December. Made good money for that one.
Yeah.
And then you got what we call spiff. If you were there and something didn't sell so many days, it was on sale, continue it. The backside of it, as an employee, you got it for half of whatever it was on sale. So, yeah, I still got a stereo at home, a realistic something. The tuners went out on it, the amps. But yeah, when you all build your little parts up, you can buy the stuff online and do okay. You're gonna pay more for it locally, but I'd check on eBay. That's where I've been buying my rolls of inductors at, is on eBay. And, this last roll I got the original equipment manufacturer's called Coilcraft. It's a Coilcraft inductor. On the Coilcraft website, it was like an inductor for 15 cents a piece. I'm sorry, I'm paying 15 cents a piece. Now, at the end of the year, I don't mind telling the government, yeah, I spent $500-600 online.
Now, it's not a case of where you just take the flat fee and then you're
No,
good.
you
You
go
gotta
flat fee, I'm declaring all of it.
you gotta
Oh, yeah.
account for all of it.
That way, if I get audited, at least that's an order, you know, then you gotta fight for the rest of the stuff. But, you know, you just gotta watch getting audited, you just don't give them an avenue.
Yeah.
I mean, you cover most of your bases. Then if you forget, you didn't claim this little 100 here, this little 500 there, go ahead and sue me. I'll pay you the penalty. But if it's a biggie, like 2 or 3 grand online, that's 20%?
You should be able to write that off as part of your business expense anyhow, I would think.
You don't count the tax off as a bit.
It's not like state tax where you can.
No.
Mm.
No, you gotta have, yeah.
What's the name of your company?
No, that's the truth. Okay, let's go to so does that help everybody on how you should do your parts? So, lots of places to look for parts. Don't be afraid to use surface mount. I like surface mount. I like surface mount. Now, if I was making a kit for somebody, it's easier to sell you a kit with leaded, because kids can do the leaded stuff, but surface mount takes more art to solder it down and not make it. But I like it. I love it. Huh?
Do you also sell kit?
I try not to, but if I do, I usually just do them at. The last kit I made for a group, I made $5 a kit. So I sold it for $50. It cost me $45. That didn't pay for my. You know how much time it took to kit the kit? Hours to kit the kit. To mark all the little color code, all the little components. I said after that, I made a run of 50 of those. After that, I swore I'd never do that again. That was a humanitarian effort. That's what that was. And y'all don't get to count time off on taxes. See? Okay, there's the input. The P is kind of modified. That's for common collector. You don't need to memorize these. We won't use these. Just use the ones we did for the common emitter. You know, this is an open book test, or what do we say? The first one's going to have a note page, but after that, it's going to be what? Open book, open note.
So note page, not 3x5.
Huh?
Note page, not 3x5. Okay.
Yeah, it's a piece of paper.
Yeah, I wasn't here, so that's why.
Yeah, it's in this class. It's a piece of paper for the first one.
And then
That's open book. So by the time you get to these, you just use your book. Okay, this I'm not so interested in you memorizing. This is your, okay. When I talk about an amplifier, we talk about its perimeters, and there's lots of different perimeters. One of them is called H perimeter, the other one's called Y perimeters, and the other one's called S perimeter. Y and H have some similarities, S is totally different. This deals with the transistors, so that's what we call a transistor model. It's a model, so those of you going on to OSU, you will do some modeling. This is the way a transistor looks like. It's a model. And a transistor, you know, is a current control device, right? So notice that you have a current here, and you have a signal coming in across there. So you're imposing a signal and causing that current change. That's why it's called a model. That's what you would do in a computer, what it was. So you do it like this. You have a node. You'd say, okay, on this node, we have a current increase of this for this much voltage or current. Well, there's 4 things going on here. This is the 4th thing. What goes in, something comes out. HFE. Beta, it's to the emitter. Right? So that one, we were using that already. We're already using HF. That's beta. We don't use the other 3 in it. Okay? The other one would be this. If I'm putting a signal in, what is being reflected back the other way? Or what's being seen? That's the input resistance. The output, when I go into this, what resistance am I seeing? That's the output conducting. And then the last one is, what if I put a signal in this direction? What leaks through it in the opposite direction? Hey, it ain't supposed to do that. All amplifiers do that. If you took an amplifier and had an in and out, turn it around and put a signal in the output, you will get a leakage back to the input. It's not supposed to have a gain. If you have a gain, you got something really weird going on. It won't have a gain. It'll be a big loss, but it was we call it leakage. It leaks through. So that is the reverse transfer voltage. Okay. So that's what H perimeters are, but only one that we do in here is the HFE, also known as beta.
If you put it in backwards, just out of curiosity, you put it in backwards.
You won't hear anything. It'll have a loss. It won't have a gain. But if you
were to amplify that,
just be lossy. So there's the general 8 model. And again, remember we refer to HFE as the beta AC. Let me go ahead and tell you what S perimeters are. S perimeters are also called scattering or F. We usually just call it. They look at the device slightly different. You will still have the forward, the feed through, the input reflection, and the output coefficient. but we will put them into an impedance. We'll put them into an impedance. So what's being reflected from the front of it may be an impedance of 25 ohms, 10. S perimeters are basically a impedance. So your idea is to match to that impedance. This is not like that. This doesn't work. S perimeter. We use a lot of S perimeters in R. Okay, you all already know about the common emitter amplifier, right? We talked about that already today. So in your reading, between now and Thursday, I want you to get the what we know as the makeup of each amplifier. In other words, what does it do? So you need to make sure you know common emitter, common base, common collector. Know all those, and we kind of went over those last semester, but this semester I'm going to test you with common emitter, common base, common collector. The common emitter is known by what we've seen today is what? That shouldn't be high. I would say medium what? Input impedance, low output impedance. It does have a high voltage and current gain. Output's taken off the collector, that's kind of obvious, and the input's on the base. It does have a 180-degree phase shift. It's the only amplifier that has a 180-degree phase shift. And you know P is equal to what? Voltage times current. So if it has a high voltage and high current gain, what's the power gain? Really high. It's the highest. This has the highest power gain. So if you all were building a power amplifier for this lab, not this lab, your next lab is your design. When you all build an amplifier for your design lab, you can see why you would probably consider the common emitter amplifier, because the common emitter gives you a lot of power gain. So there's advantages of using the common emitter. Your task would be to what? Make the output dump to a watt ohm. What do you think I'm going to use for a load? Now, speaker, right? We're going to hear it. 8 ohms. That needs to see 8 ohms.
There's a phase shift, is there a slight bit of delay?
No.
If
You
you,
won't know
if you had something to measure it, would
The only time the phase shift hurts you, if you're using the phase shifter. Let's say you were using the phase to knock down the gain. Well, if you put two phases together right in a row, 180 in, another 80 in, then you're back in what? You're back in phase. So if that was driving something like you were broadcasting to the telephone, if it kept adding, then it'll go into oscillation. So, but if I wanted to get rid of that, I on purposely would use some phase shift to knock that down. Push-pull amplifiers or something we can do to knock that down. 2 transistors, you on purposely run a small resistor there. What that will do is that will feed that 180 back on there. That will kill some of the gain. So what you do is you do enough of it to get rid of the oscillation and not kill the good gain. So remember, we sacrifice gain for what? Stability. And that'd be the way to do it, is put it from there to there. Or something. I put a little bitty capacitor from there to there in RF circuit. Because as frequency goes up, what's X sub C goes down. So as you go higher and higher in frequency, guess what's feeding back over to here? The output back to the input. How many degrees out of phase is it? 180. So guess what? My signal, it drops. So where it starts trying to oscillate at, it's also the gain is starting to drop, so it quenches the oscillation. Okay, so those in your book, that's chapter, that's partly 6 and partly 7. Partly 6 and partly 7. So you want to go over each one of those. The common emitter, the common base, right there, common base, which has a low input impedance and a high output. And of course the collector, which is also known as a what? Emitter follower, right? Emitter follower and common collector are the same thing. I like the emitter follower. It automatically gives you a low output. It's a low output impedance, high input. But does it have a voltage gain or a current? Gives you a good current. You what? No voltage. Has a gain of. So what goes in comes out. 2 volts in, 2 volts comes out, or a little less. But you gain a lot of current. On current, which your speaker wants what? Current, because it's low impedance. Low impedance wants current. So this one does pretty good. It's not real efficient though. It will get hot. And we won't get into efficiency so much this test. And the second test, y'all's second section, when we get into the amplifier, we'll get into efficiency.
2 volts in, 2 volts out, high current.
Okay, let's say the 2 volts that you had was off the guitar. Not a lot of current there. If there's 2 volts on the oscilloscope, as soon as you hook a load there, guess what happens at 2 volts? It goes down real low, right? Because we'd call it probably like a 600 ohm impedance. So you take a 600 ohm impedance and hook it to an 8 ohm speaker, it's gonna take it from that big all the way down to like that big. You go, I'm losing my signal. You have 2 options. You either run the 600 ohm 2 volt peak to peak signal to an amp, like a big amp, run it on up to, let's say, 30 volts, and then let it squish it back down. Or you can take the 600 ohm 2 volt peak to peak and run in that amplifier. Now, you didn't gain any 2 volt, but you didn't lose your 2 volt. Because as soon as you hook that to a load, the input's going to stay this big, the output's going to go that big. So remember, before the output was going like that, now it's going to stay there. So did you gain anything? Technically, no. But did it not amplify? It amplified. It maintained, which means it amplified, because you went from there to there, back up to here. So technically, it is an amplifier. It's just not a what? Power amplifier. There's only one true power amplifier, and that's the common emitter. The common emitter is the only true power amplifier. All the rest of them are types of amplifier. That is a type of amplifier. That's like an impedance matching amplifier. It's to get because the input impedance, this guy is like 10K or something, right? So you hook your 600 ohm guitar amp up to this. Well, this input impedance is so high, your guitar amp goes, man, that feels good. I'm not getting loaded down, right? So if you say you had 2 volts peak to peak, it doesn't drop. It kind of stays close to 2 volts peak to peak because it thinks it's not hooked to anything. See that? This amp blinds you from the load, right? This amp is like a buffer. Remember, we used the term buffer before. We will at RF class. We use a lot in RF. That's a buffer amplifier. So this side is happy-go-lucky. It doesn't change. It's going to say, okay, I'm going to take whatever voltage you give me. I'm going to hide you from this high current over here so you don't drop. So this over here stays at 2 volts, and it's just going to maintain the 2 volts out here. So you did gain something. You gained impedance match, so you could hide more current. No, you didn't gain power.
Well, does this push the speaker?
It pushes the speaker really, really good now. Without this amp, your 2 volts at 600 ohms, as soon as you hook it to an 8 ohm speaker, it's gone. It won't power anything. So this acts as a buffer. It protects that side from that side, and you get current gain. You just don't get voltage. So you need to really think of the emitter follower, the common emitter, like a buffer amplifier. That's kind of what it really is. It's more of a buffer. It separates 2 sides, and it gives you something. It gives you current gain. The common base is just the opposite. The common base takes a low impedance and drives a high impedance, which is kind of weird. But you might use it on tube amp, see? Because a tube amp might want high impedance, right? Well, what happens if I have a low current, a low voltage, high current source? I have a low voltage, high current source, right? Now watch this. Let's say that was 2 volts, but let's say it's like 5 amps. It can handle 5 amps. I could have hooked it directly up to the 8 ohm speaker. See? I could have done that. So this amplifier didn't do me any good now because I had a low impedance driving it. It didn't do me no good. I could have hooked directly up. Now let's go the other way around. Let's say my load is 10K. Let's say my load is 10 kilo. Okay, and I'll give you an example of what that would be. That would be like a thermostat or something. I was trying to turn on a thermostat. The thermostat had a high impedance. Okay, so out here is a low impedance, 2 volts. The thermostat wants a high impedance, let's say at 30 volts. 2 volts in, 2 volts out. He didn't get anything. But if I use a common base amplifier, 2 volts in will give me 30 volts out. The common base is a what? It's a voltage multiplier. This is a current multiplier. The common base is a voltage amplifier. And you can tell nowadays why we don't use common bases. I mean, we don't use it. Kind of think of a time when you need to turn a low impedance to a high impedance, high voltage. That's abnormal. That's not normal nowadays. Most everything nowadays is lower impedance, so you don't gain a lot. Now, back in the day when we had vacuum tubes and stuff, when we had higher impedances, it might make sense to take your guitar pickups that were low impedance and run it to a common base so you can drive higher voltage to the tube, see? Because a tube wants voltage. It don't want current. So that would drive the tube hard. But we don't use them as much anymore, so, and there's other reasons. We just don't have common base configuration is kind of not normal. Not many people. The most common is common emitter. Like 90% of all circuits are common emitter. Then emitter follower would be like the other 9%, and then 1% would be common base. That's kind
Okay, one's voltage gain and the other current gain.
Yes.
Collector emitter.
Common collector. Common collector is Common collector is current gain.
No, the CE,
That's common emitter.
common emitter, so
That's-
that's.
That's both. That has voltage and current gain. So therefore, it has a huge power. These only have medium power gain. They're medium. They don't have, it's not high. This is a medium power. Because if I have a voltage gain of 1, I have a power gain of 50. 50 times 1 is 50. So it has a power gain of 50. Now let's take a common emitter amplifier. Let's say it has a voltage gain of 20 and a current gain of 20. It's 400, right? So it has a power gain of 400 versus 50 of this. So obviously the common emitter has a high power gain. But what I was gonna, and we really need to wrap up, but what I was gonna allude to was this. When you all start thinking about building your amplifier here in the next 3 or 4 weeks, is this. If the common emitter has this great power gain, and you've got this 1 kilo ohm resistor there, how are you gonna take that 1 kilo ohm and drive a what? An 8 ohm speaker? You're gonna have to run a buck. Or do this. Build a resistor that matches the impedance. What's wrong with this circuit? What happens when I lower the resistance? What's gonna go up?
Current's gonna go up.
Current's gonna go up. This thing's gonna run hot. It's gonna run hot as snot. As running a fever snot, okay? Not a good idea. Only a young, educated pup would do this. So don't do this. This is your last resort. This is the one that got drunk the whole month of February and came into class like an hour ago and wanted to enter something.
I'll mentally note that.
Which will not get you a very good grade.
Can only hope.
What's that do?
Matching.
Matching impedance. And what is the losses of the transformer compared to the resistor?
They're pretty horrible.
Pretty small. In other words, a transfer considered to be lossless. Or it's low losses, all right? It's not loss. It's low losses. But it shouldn't get hot. The resistor will get hot. This is like light years, speed ahead of the other one. This will get you a 20 to 25 efficiency rating. Guess what the resistor would have got you?
5.
3 to 5%, not over 5. Light years.
Do you have any like distortion or phase shift
You
issues?
can, remember back in AC, we didn't really talk about it. It was called those B&H curves and transformation, blah, 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 blah. Unless you're in England. If you do hit too much current through it, you will saturate the core, which will give you clipping. But I think at the current that you all are going to be running here in the lab, even those little bitty transformers are like that big, audio transform, we'll talk more about transformers and which ones to use. See you all. Remember, Thursday is labs. You come in, all you're doing is lab. There is no lecture. No lecture on Thursday. Zippo. Okay? We'll lecture again a week from now.
I think he's gonna get us the copy. Is he gonna print it up right now?
Yeah, I think it just needs like 1 more.
Okay, okay, that's the deal. Huh? Yeah, right, yeah, I got talking about a bunch of stuff.
Anybody else need a copy?
I need to make a week of materials. Can't believe I thought the class started this week.
You just need a syllabus.
Syllabus,
Just get you a syllabus and then look in the book, and the book will tell you what kind of components you need.
okay. Should I have a copy of anything you've been through, a PDF or a PowerPoint or anything to make sure I hit the right stuff?
I don't do them. I mean, I don't have PowerPoints to give out. Once in a while I do, but I haven't so far. I would just go over the book.
Syllabus, yeah, okay.
Yeah, and look at go over chapters 1 through 4.
Okay.
Yeah, 1 through 4, 1 through 5. My syllabus must be down in my office, so let's go down.
Okay.
So I gotta go down there and make a copy. Yes, I do.
Oh, man.
I got the biometric class, but I'm sorry. Just ask people.
Do I need to bring any breadboards or anything for the lab?
Yeah. breadboards and pick up a parts kit over in the bookstore. It's a little brown box.
Oh, okay. Is the bookstore open right now?
I think they close at 7,
Oh,
so.
well, it's pretty soon here.
So what happened Saturday? You said you never heard anything.
Well, you kind
Ah, there's the syllabus right there. Okay, there's that.
All righty. And I'll
That tells
pick
you
up
everything
the,
there to give.
okay, I'll pick that up at the bookstore. We should be good?
Yep.
All right, thanks very much. Where did that come in at?